Today, we are undertaking a deep dive into, well, the very infrastructure that dictates how we manage our planet's most critical resource, fresh water. We're talking about stream gauging stations, those seemingly simple structures you see on rivers worldwide.
Yeah, they look simple, don't they?
They do, but they're fundamentally important. By measuring the water level surface elevation, experts can estimate the volumetric discharge, or, the flow.
Mm.
And this data, this sort of constant pulse check on freshwater systems, it forms the basis for pretty much everything from water allocation decisions and forecasting flood or drought risks to analyzing crucial long-term hydroclimatic trends.
Absolutely. That data is crucial for every nation, really. But the research we're looking at today highlights a core problem. While these gauges are vital for local and national needs, when we zoom out to the global scale, well, their placement may have inadvertently introduced massive systemic biases.
Right. Biases in what we're actually measuring globally.
Exactly. So we're diving into the findings of the paper Assessing Placement Bias of the Global River Gauge Network, which was led by Corey A. Krabbenhoft. The mission here really is to understand precisely where those biases lie in the global stream gauge network's spatial distribution, and critically, what the lack of equitable representation means for global water security and conservation efforts.
Okay, let's unpack how the researchers even approach this. Quantifying bias across nearly the entire global river system, that sounds like millions of river segments. It just seems like a monumental task. How did they possibly capture that scale and quantify what was missing?
Yeah, the scale is huge. It definitely required leveraging some pretty sophisticated global data sets. The baseline they used was the global reach level a priori discharge estimates for surface water and ocean topography, or grades. You can think of it like a huge inventory.
Grades, okay.
Right. And this data set provides modeled flow estimates for nearly 3 million river segments. Though for this study, they specifically focused on segments with drainage areas greater than 25 square kilometers. So think of that as the comprehensive map of nearly every significant river segment globally that they were working with.
So they had the sort of complete picture, at least down to that size.
Yeah.
How did they then figure out the characteristics of all those rivers to compare?
Well, they combined 3 key pieces of data. First, they mapped about 32,091 existing stream gauges onto that grades network, so where are the current monitors?
Got it.
Second, they integrated comprehensive data from the HydroATLAS database. Now, this provided a suite of 13 geospatial attributes, things like climate, the slope of the land, socioecology, human influence metrics, for every single river segment in the study.
Okay, so characteristics for every river gauged or not.
Precisely. Essentially, they were comparing the environmental characteristics of those 32,000 or so gauged rivers against the characteristics of all 3 million rivers in their base map.
So just to simplify this for you listening, they weren't just counting dots on a map to see, where the gauges were physically absent.
Yeah.
They used a sophisticated mathematical tool, right, to determine if the characteristics of the rivers with gauges accurately reflected the characteristics of all global rivers.
That's the key distinction.
Yeah.
Exactly. They used a statistical measure called the Wasserstein distance. It basically identifies the disparity or the distance between the statistical distribution of conditions in the gauge segments versus the distribution in all segments.
Okay.
And this allowed them to pinpoint exactly which environmental traits, whether river size, climate, proximity to human activity, you name it, were statistically over or underrepresented in the network we actually have.
That makes perfect sense. Now, I understand one specific challenge they had to tackle was defining whether a river was, well, flowing or not, especially for intermittent rivers. They had to create a critical measurement, flow permanence.
That's right, yeah. Flow permanence was defined as the proportion of days a river segment had active flow between 1979 and 2013. The methodological challenge, as you said, arose because modeled data, like grades, rarely reports a perfect zero flow even when a river might be dry in reality.
Right, it might show a tiny trickle in the model.
Exactly, it might report a tiny negligible discharge. So the researchers had to establish a specific low discharge threshold, I think it was 0.16 cubic meters per second, to count a river segment as effectively not flowing. It was an acknowledgement that modeled data is limited in detecting true intermittency, but they needed a way to capture how consistently a river runs.
That's a great demonstration of the complexity involved in this kind of global analysis. Okay, so based on all this work, what types of rivers are currently getting the lion's share of attention? What did they find was statistically overrepresented in the global network?
Well, the results immediately confirmed what many suspected. the human-centric bias. The gauge network overwhelmingly favors rivers that are important for existing management and large-scale development.
Right. Things we actively use or manage.
Precisely. So we see a huge overrepresentation in terms of size and flow. Gauges heavily favor large rivers, those with a high Strahler stream order.
Okay, just for clarity, when you mention Strahler stream order, you're referring to the size and branching complexity of the river, correct?
Yeah.
So a high order means a big trunk river, like the Mississippi or the Amazon.
Exactly right. They favor these large rivers and perennial rivers, those with high flow permanence, meaning they run pretty much constantly, which, is logical on one level. We need to monitor the big, continuously flowing water sources for cities, for industry.
And I'm guessing that infrastructure logic kind of guides the rest of the findings, too.
It really does. Gauges disproportionately monitor highly dam-regulated rivers. No surprise there. They also prioritize watersheds with high population density and a large human footprint, which is their composite metric for various anthropogenic influences. And then in terms of climate, the network favors mid-latitude and mesic climates, so the temperate, wetter regions of the world where historically a lot of development has occurred.
And this is where it gets really fascinating, isn't it? Because the very logic that guides local placement, put the gauges where the people in the dams are, is the exact thing creating this global distortion.
Yeah.
The cumulative effect is a global network that fundamentally reflects human infrastructure needs much more than it reflects natural river diversity.
Yeah.
And that surely undermines our ability to draw accurate global scientific conclusions about rivers as a whole system.
It absolutely does. That lack of natural diversity in the monitoring system has profound consequences, especially when we start thinking about global change, climate impacts, biodiversity.
Okay, so if the network overwhelmingly reflects human management needs, what types of river systems are we fundamentally overlooking? Where are the critical monitoring blind spots identified in the paper?
Right, the flip side. The underrepresentation is, perhaps worryingly, highly concentrated in areas critical for both conservation and climate resilience. Let's start with conservation.
Okay.
Rivers with a high proportion of upstream protected areas and, crucially, free-flowing watersheds, the places most critical perhaps to preserving natural riverine biodiversity, they're sparsely monitored.
So the wild rivers are being missed.
To a large extent, yes. And if conservationists have no reliable long-term monitoring data on flow regimes in these areas, they really struggle to develop realistic, science-based conservation and restoration goals. It's hard to effectively argue for protection or against development if you can't quantify the ecosystem services of the natural system you're trying to protect.
And it's not just about protected areas, right? It's also about the scale of the rivers themselves.
Yeah.
Small streams.
Yes, absolutely. Small rivers, headwater streams, are massively underrepresented across all habitat types. Now, why should you care about these little streams? Well, because headwater streams, while small individually, collectively, have a disproportionately large role in critical watershed functions, like nutrient processing, carbon cycling.
The basic health of the whole river system starts there.
It really does. Our global understanding of the basic functions of river ecosystems is compromised by this blind spot. And importantly, the researchers stress that this bias against small rivers is actually much worse than their study could even show. Remember that initial 25 square kilometer minimum watershed size limit they had to use?
Right, because the grades data didn't go smaller.
Exactly. So the really tiny headwaters weren't even in their analysis to begin with.
Wow. Okay, so that means we're missing data on potentially millions of the planet's smallest yet ecologically vital streams. What about flow type? You mentioned perennial rivers are overrepresented.
Yes, and flow type is perhaps the most urgent gap right now, given climate change. Non-perennial flow regimes, that means intermittent and ephemeral streams, the ones that regularly dry up for periods, are strongly underrepresented.
And that's a huge problem.
It's a massive problem because these types of rivers, these non-perennial systems, they're becoming increasingly prevalent worldwide due to climate change and shifting precipitation patterns. Our current infrastructure is fundamentally designed to measure flow in rivers that run all the time. It's simply not set up well to measure the complex hydrology of systems that dry and re-wet frequently.
Okay, so small streams, intermittent streams, and finally climate extremes.
Yes. Gauge coverage in extremely hot or cold regions, what the study refers to as polar and xeric freshwaters, is relatively sparse. In fact, the greatest overall bias statistically occurred in those regions.
Was just to confirm for you listening, xeric essentially means extremely dry or arid, right? Like deserts and very dry grasslands.
Precisely. And this is where we see that kind of interesting contradiction emerge. The study found that the tendency to place gauges on regulated rivers, like behind dams, was greatest in those very xeric arid regions.
So where water is scarcest.
Exactly. Where water is so scarce, they have to monitor every drop that goes through a dam or a major diversion. So the local need for management data is incredibly high, driving gauge placement there, yet the overall coverage of diverse natural river systems in those same arid regions remains extremely low.
So pulling this all together, what does this mean when we look at the big picture implications for global science? This disparity sounds like it fundamentally weakens our understanding of global water cycles, elemental cycles like carbon, and surely compromises efforts to achieve global biodiversity goals.
It absolutely does. And the disparity creates a looming crisis for hydrologic modeling, too. Think about it. If we train our forecast models only on data gathered from large, wet, perennial, and often heavily regulated rivers.
The models learn from a biased sample.
Exactly. Those models then fail, sometimes catastrophically, when they're applied to the increasing number of intermittent and ephemeral systems or small headwaters or rivers in extreme climates. You simply can't reliably predict drought impacts or flash floods in a complex, arid watershed using a model that has only ever seen continuous flow data from a temperate zone.
So the models aren't ready for the future climate, is bringing us.
In many ways, no. The paper argues quite strongly that investing in monitoring these environmental extremes now, like those intermittent streams, the polar regions, the arid zones, will dramatically improve future modeling efforts precisely because these challenging conditions are becoming, the new global normal in many places.
Okay, so if we agree that ripping out existing vital gauges isn't the answer they serve critical local needs, what did the researchers propose as the smartest strategy for installing new ones to fix this bias?
Yeah, it's definitely not about removing gauges. It's about being smarter with new ones. They advocate for a targeted prioritization strategy. Using their analysis, they identified priority geographic areas where adding a new gauge would yield the greatest global reduction in bias per gauge added.
Maximum bang for the buck, globally speaking.
Kind of, yes. And these areas are typically arid regions, often corresponding to those xeric areas we discussed, including large swaths of Western North America, Northern Africa, Central and Northern Australia, and the Eurasian steppe. The key takeaway here is really important. Simply adding more gauges on larger, already overrepresented rivers contributes almost nothing to reducing the global bias. We have to be strategic about where we spend our limited resources.
And beyond just building more traditional concrete gauging stations, the study points to some alternative monitoring strategies that could help close these gaps, maybe more quickly or cheaply.
Absolutely. One major opportunity they highlight is leveraging advances in remote sensing technology, particularly satellite observations, especially for monitoring those large, already overrepresented rivers.
So use satellites for the big rivers.
Right. If we can reliably monitor the discharge of major trunk rivers using satellite data, that potentially frees up limited in-stream gauging resources, the money, the personnel, allowing them to be strategically shifted to installing and maintaining gauges on smaller, currently underrepresented rivers.
Makes sense. Anything else?
Yes. They also mention leveraging community science efforts, citizen scientists, to provide valuable, maybe less continuous, but still useful data for the thousands of smaller systems that currently lack formal infrastructure, getting local communities involved.
That's a growing field. But there's a geopolitical reality here too, isn't there?
Oh, definitely. We have to acknowledge that. Many of the most underrepresented areas, these priority zones for new gauges, they occur in countries that face major economic or governance challenges. You're talking about parts of Africa, Southeast Asia, Central and South America.
They might just not have the capacity or funds.
Exactly. They simply may not have the national capacity to significantly expand their hydrometric networks without substantial financial assistance and international cooperation. The paper mentions initiatives like the World Bank's National Hydrology Project for India as a good example of the kind of collaborative effort that's likely needed in many places.
So that brings us full circle, really. The globally driven process of building these monitoring networks, guided largely by immediate, local human needs for water management, has inadvertently created this biased system. A system that, when looked at globally, fundamentally fails to provide the balanced, comprehensive data required for understanding and protecting the global environment as a whole.
And that data deficit, as the paper implies, is a huge strategic vulnerability for all of us. We know now, based on this analysis, that just adding more gauges on the big, familiar, often dammed rivers contributes very little to reducing the overall global bias. So this raises a really important question, I think, for you listening, and certainly for everyone involved in water policy, science, and conservation.
What's the trade-off?
Exactly. When facing inevitable limitations in budget and resources, how do we effectively balance the immediate, undeniable local need for water management data in highly populated, developed areas, with the broader, arguably just as critical long-term scientific need to monitor and protect the world's vulnerable, free-flowing, and increasingly intermittent waters? What are we willing to prioritize today to better understand and manage the water challenges of tomorrow?